Thank you. I'm pleased that we can, get right into the program now with our first keynote. So I'd like to introduce Talia Ringer, an assistant professor at UIUC, who builds technologies for developing and maintaining verified software systems using techniques ranging from dependent type theory to machine learning and everything in between. Talia was also a visiting faculty researcher at Google in 2022, working on language models for formal proof. Talia earned a PhD from University of Washington in 2021, and prior to that, a BS in computer science and mathematics from the University of Maryland. Then worked as a software engineer at Amazon for 3 years. They've received the SIGPlan Distinguished Service Award and the DARPA Young Faculty Award. The title of today's keynote is Language Models for Formal Proof. If you're watching on Ring Central, if you have any questions, you can put them in the chat and I should be able to see them. And so without further ado, I'd like to turn the floor over to Talia.
All right, thank you for the introduction. So my name is Talia, and I'm going to be talking about language models for formal proof. So what I mean by formal proof here, these are proofs that are developed using these special tools called proof assistants. So these are the way these tools work at a really high level is that you can write your program inside of these proof assistants. Then you can specify something that you want to be true about your program. And then if your program actually does meet that specification, you can write a proof that shows that your program does meet that specification. The proof assistant will check this and let you know that your proof is correct. So your program is verified. Now, these proof assistants have come a long way since they first came out, especially when it comes to this last step here of actually writing this proof. So this used to be so hard that even experts would only verify toy systems, but it's gotten much easier. And so in the last couple of decades, we've seen experts use these systems to verify things like compilers, file systems, web browsers, machine learning systems, operating systems, and even a quantum optimizer. So they come really far, but it's still a lot of work. So one of my favorite examples, there's this cell 4 verified operating system microkernel. And this development took a team of proof engineers, about more than 20 person years, and spent more than 1 million lines of proof. So that's a lot of effort. So what a lot of my work is on is in building automation, proof automation, that makes it easier to develop and maintain verified systems using these proof assistants. And traditionally, I would use tools like symbolic proof automation, things from programming languages, from old-fashioned AI to build this automation. And this had some huge benefits. It's predictable, dependable, understandable, but it also was limited in scope to just what you defined it to work for ahead of time. And it also takes a lot of expertise to extend if you want to actually expand that scope. Now, on the other hand, recently these language models have become like pretty popular. They're a pretty big thing now. And you can build automation using language models, and it tends to have the exact opposite set of trade-offs. It's unpredictable, not dependable. You don't really know what's going on inside. But on the other hand, you don't need to define the scope ahead of time, and it takes very little expertise to extend it to something new. So what I would really like is to get the best of both worlds here, to get all 5 of these things. And so that's talking about today, because I want us to get to this future where building something even like this cell 4 verified operating system microkernel is hopefully not that much work, and there's a lot of computer help, and it's not an unpleasant process. So I'll be talking about that today, with both kinds of automation and how we'll bring them together and the opportunities this presents. But I want to start with a little more background on these proof assistants, just in case people haven't seen these before. So I'm not going to be showing you kind of like a verified operating system microkernel for the sake of this talk. I'm going to start with a really toy example. So we're going to show that the list zip function preserves the links of the inputs. Now, it's worth noting that even though this is a toy example, large verified systems are often made up of lots and lots of smaller functions that are verified. And so it is still quite realistic. And the proof assistant that I show you this in will be the Coq proof assistant, because this is what a lot of my work focuses on. It's the one I'm most familiar with. Now, when I show you things in Coq, I'm going to translate the syntax a little bit, make it a little like Java or C-like, just because it might be unfamiliar to people who haven't used a language like it before. So in order to verify this function, first we need the list data type to begin with. This is something that we get out of the standard library. So a list is polymorphic over some type T. So we can have a list of numbers, a list of characters, and it's one of two things. Either it's empty, or it's the result of taking some element and some other list and just sticking that element in front of or consing it onto the rest of the list. Now, also in our standard library is the length function defined over lists. And this is defined in a pretty standard way. If the list is empty, then the length is 0. And otherwise, if we have something in front of some other list, just one element in front of a list, then to get its length, we're just going to add 1 to the length of everything that follows. So it's a recursive computation that calculates the length of this list. Okay, now that we have these library functions, we can actually write our zip function that we're going to want to prove something about. So our zip function is going to take 2 lists of inputs. These lists can be of potentially different types, L1 and L2, and it's going to combine them into a list of pairs. So the way, if we have our 2 list inputs are 1, 2, 3, 4, and X, Y, Z, then our zip function is going to return 1x, 2y, 3z. Now, one thing that's worth noting here is that we have to make some decision about what to do with this extra 4 at the end here. Like, what do you do when your list inputs are different lengths? And the decision that this zip function makes is to just ignore these extra elements. But the way that it works is otherwise pretty standard. So if either list is empty, it just returns the empty list. And otherwise, it's going to take the first element of each list, combine it into a pair, and then stick that in front of, cons it onto, the result of recursively calling zip on the rest of each list. Okay, so when we have our zip function, we can get to the interesting part about using these tools. We can specify what it actually means for this function to be correct to us. And so we're going to specify that zip preserves the lengths of the inputs. And we'll do this by stating a theorem. And this theorem is actually like in the same language as the function that we just wrote. And what we can do is we can actually quantify over all possible inputs that we could have to this function. So here we say for every input L1 and L2, if the lengths of those inputs are the same, then the length of the output of calling zip is the same as the length of one of the inputs. Now, another thing that's worth noting here is that this process of choosing a specification, of stating your theorem, this is a bit of an art. There are many things that can be true about your function. And so, for example, we could just as well have chosen this theorem, which says that the length of the output of calling zip is the minimum of the lengths of those 2 inputs. This is also true. And in fact, it's stronger. It implies the other specification, the one that we actually stated. But nonetheless, whichever we choose, Coq will send this back to us as the goal we have to prove. And then we actually get to write this proof to actually show that our function satisfies this. And if we wanted to, we could actually write this proof directly as a giant function in that same language that we wrote our program and our specification in. In Coq, that language is called Galena, and that would be called a proof term. So we could just write a giant function, actually, that satisfies this, or that proves this theorem, whose type actually turns out to be the theorem that we've just defined. But this is really hard. People tend not to like doing it. We're not used to thinking about these really fancy functions with these really fancy types. So instead, this is where traditional proof automation comes in. Now, proof automation here, at least as traditionally used, is a little bit of a misnomer. It tends to be more like an interactive or assisted process, which is why we call these things proof assistants. But one really traditional kind of automation, these things called tactics, the way that these things work is that when Cox sends this back to you as the goal you need to prove, then you drop into this interactive proof mode. And in this interactive proof mode, you will send these kind of high level strategies called tactics. So that might be something like do induction over one of the inputs. Then Coq will respond by refining your goal into some sub-goal. So it might say, prove the base case. Then you'll respond with more tactics. So you might say the base case holds by reflexivity. Then Coq will respond by refining your goal again. Like maybe it'll say, prove the next case. And this process of these tactics and these refined sub-goals, this will continue and continue, all the while you're building up something called a proof script. So this is a sequence of these tactics, of these strategies. And that's kind of what you see as a proof. But it continues until, like, this proof script is only really done. You can only write QED when Coq has found a proof. And when Coq has found a proof, what that means is that it's able to take this proof script and basically compile it down to that proof term that you could have written to begin with, that giant function in the original language that it can check to make sure that it really proves your theorem. And it does this by just checking its type and making sure that the type of that is the theorem that you stated. If that's true, it can let you know with certainty that your proof actually holds here. Your list zip function preserves length. But you don't have to see this kind of low level function. You don't have to write it yourself. You get the abstraction of writing these high level proof scripts. So this is what it looks like in actual Coq. This is just one proof script I could have written for this theorem on the top with the abstraction. And then at the bottom is actually the proof term that Coq finds that corresponds to this. And I've highlighted corresponding parts. Now I'll focus on just one of these just so you can see how they do correspond. Here, I'm inducting over the second input list. And what this actually does is it compiles it down to this function that's called an induction principle. And these are defined automatically for every data type, like a list, a number. So for lists, it says, if I can show some property about the empty list and, given some property about an existing list, I can show it about sticking some element in front of the list as well, then I can show it for any list. So it's kind of like the induction principle for natural numbers, but it's over lists. And then it breaks into two cases. And at the top level, you see these are bullet points, the plus marks, where I'm using these tactics. And then on the bottom, these will compile down to terms as well. And these terms don't matter too much. They're just kind of reasoning about equality, some rewriting, some simple terms about equality. But this is what is really happening under the hood. And so the automation is kind of abstracting away these low-level terms. So this is just one kind of traditional proof automation. There is a lot more. Things like reflection, custom tactics, custom proof modes, proof procedures, plugins, proof repair, which I'll talk about a little bit later, and these things called hammers. What's really important, though, is that this automation can do basically anything and yet still preserve correctness. Like, we don't have to worry that much about what it's doing. And that's because of this design principle for these proof assistants called the de Bruijn criterion. And what the de Bruijn criterion really is a separation of concerns between the thing that produces the proof and the thing that checks the proof. So what produces the proof, this could be search procedures like these tactics. It could be domain-specific heuristics. It could be transformations that take in existing proofs and transform them to new proofs directly. It could even be something like ChatGPT, any language model. We don't have to worry that much about what these things are doing, because in the end, we have something small and human readable that's actually going to check the proof that's produced for us. That proof term is going to be checked. And that is that thing is called the kernel, the thing that does the checking of the proof. And it's a small logical kernel. Um, and this is the part, in Coq, this is the type checker. This is the thing that gives us certainty while we get this abstraction. So this could be, a proof script, but we could also write our automation in OCaml. A lot of my automation is written this way. We could use ChatGPT here. As long as we don't touch the kernel, our automation is safe. Now, there are some asterisks here. First of all, our specification has to be okay. Um, and it's only going to check that it satisfies the specification. It's not going to check our specification. That's not even really a well-defined thing to do. Also, our kernel shouldn't have any bugs. That's why it's supposed to be human readable. And you should not introduce any axioms. If you introduce new axioms, then it's on you if you introduce two things that are kind of contradictory in some way. But essentially, the kernel and the specification are the core trusted pieces of all this, which are vetted by humans. On the other hand, the rest of the system is trustworthy inherently because of this separation of concerns. Okay, so I've shown you some traditional automation, which tends to have these benefits. But I want to give you an example here with some of the work that I've done on proof repair, and kind of show you how it has these trade-offs. So proof repair was the topic of my thesis work, and a lot of papers that we kind of wrote along the way. And the problem that proof repair is solving is dealing with kind of changes that break dependencies. So, say that you are depending on the Coq standard library, and then they change a data type or some kind of specification there, then everything that depends on it, you could break the programs, the specifications, you can break the proofs. And so proof repair is looking to automatically fix those broken proofs in response to changes. One class of changes that I've looked at is certain kinds of changes in data type. So for example, let's say we change a data type and we break the whole standard library in Coq. With our tool, which is called Pumpkin Pie, for this particular change I'll show you, we can actually automatically fix all 451 broken functions and proofs in about 25 seconds, completely automatically. But this is going to be a really toy example. All we're going to do is take this list data type that I've shown you and just kind of swap two constructors so that now the cons constructor comes first. This actually does break 451 functions and proofs, but you can just call Pumpkin Pie and it will fix all of them for you. Now, this is a simple example. There's a lot more that Pumpkin Pie can handle. But I think what's important here is that what we get is predictable and dependable. So when I say by predictable here, I can define exactly what Pumpkin Pie supports ahead of time, and it's always going to work on those. And it's not going to do anything super weird. It supports any change that can be described by something called a type equivalence. Now, a type equivalence is something from homotopy type theory. Basically, whenever we have an isomorphism, so two functions between here two versions of our data type, like the old list and the new list. We swap the constructors and we swap them back. And they're mutual inverses. So, when we call swap on the two constructors and then we swap them back again, we get the original list. And similarly in the opposite direction. Whenever we have one of these isomorphisms, we can construct an equivalence between the old and new version of our data type. Pumpkin Pie in that situation, sometimes will actually discover this equivalence for you, just given those two types, like these versions of list. Sometimes you have to give it a little more information, and sometimes you have to give it the equivalence itself. But in either case, it will take the old version of your function or proof, and it will actually transform it to some new function or proof defined over the new data type that doesn't reference the old one at all, doesn't even call functions that convert between them. So It turns out to be also dependable. It's flexible. It's useful for real scenarios in those use cases that it's designed to work for. Because it turns out that these equivalences are like more expressive than they may sound at first. So if you don't look just at equivalences between the old and new version of the data type, but you start to look at an equivalence between the old version of a data type plus and the new version with some additional information or something like this, then you can handle adding some sorts of new behaviors, new information to your data types. And you can still repair things that way. But then there's just a little more user input that's involved. A third positive that comes out here is that it's pretty understandable. We know exactly how and why it works. Although I put an asterisk here because I think it's really understandable for type theory nerds. Like what it really does is implement something called transport. This comes from homotopy type theory. It's really like a fancy way of rewriting functions and proofs across equivalences so that they still have the same behavior up to the equivalence. And it does this as a proof term transformation. So rather than follow the equivalence, by calling the functions and the proofs that make up the parts of the equivalence, it will actually take things defined over the old data type and transform them directly to things defined over the new data type. So it doesn't have to keep around the old versions after every incremental change. And we also know why this works. It works because we can destruct any equivalence between two types using this theorem called Lambeck's theorem into things that talk only about each of these types. So only about the old version, only about the new version. And then we just transform things in a pretty syntactic way that referred to the old version to things that refer to the new version using this deconstruction. But we also see these negatives come out. So it's limited in scope to just these equivalences, just what I've defined ahead of time. Now, recently, I have a paper that's under submission with two of my students where we tried to extend this scope. And we extended it to one class of changes, these things called quotient type equivalences. And we did this successfully, but essentially, quotient type equivalence just lets us express like more complicated changes in behavior that we couldn't express with plain equivalences. One example we handle, for example, is say we have a version of a queue that just has one list that's backing it, and a version of a queue that is backed by two lists and is able to have some optimizations because of that. We're able to take the proofs that these things are actually queues and repair them across this change, even though they're kind of more behaviors to this two list version. But you know, this took a ton of expertise to build this extension for this well-defined class of changes. In particular, this was between me, one of my PhD students, one of my undergraduates, and it actually took 2.5 years to get this working and to get automation for this. So, a question that comes up here is this really sustainable? Are we gonna, for every kind of change that we want to support, take 2.5 years with, a bunch of experts? And I think this is one place where these language models are really exciting. So this is something that I've been thinking about a lot recently because it seems to have the exact opposite set of trade-offs. So, we've done a bunch of work with this. A lot of this work is with some of my collaborators at UMass Amherst, at UCSD, at Google over that summer. Um, I want to start actually with my first example or my first experience using any language model to do proof automation. This paper on Passport, just to talk about these trade-offs. Now, this was with a small language model. It wasn't a large language model. It was kind of specifically a language model that was built for proofs by academics, but we still see a lot of the same exact trade-offs come out. So what we were doing here is there was a small language model that was being used to sort of predict the next tactic inside of these proof scripts when people are actually writing these proof scripts. And we realized there was a lot of information that they weren't using about identifiers, dependencies, how these things are related. So what we did is we just kind of, extended this. We added more of this information into the model, encoded more information, and then we used it to improve the tactic prediction model. And the positives stood out pretty much immediately. So with respect to scope, we trained and tested this on a benchmark suite called CockGym. This is a benchmark suite that includes mathematics, it includes verified programs, it includes automation libraries. It spans 123 open source Cock projects. We trained on 97 of those projects. So that's almost 58,000 theorems. We tested on 26 of those projects. That's almost 11,000 theorems. And despite this massive scope, we were able to see really clear improvements. We were able to immediately prove like 45% more theorems than before, getting a little over 1,800 of these theorems proven. And we also found that when we started combining some of these models, so different extensions, different models actually turned out to prove different things. And so, one really cool thing about these proofs is that since we have an oracle that's actually going to check the proofs, we can just run these in parallel and take the union of these. And when we do that, when we take advantage of this diversity, then we were able to prove 64% more theorems on the baseline. And then we're getting up towards like 2,000 of these theorems. It was also really easy to extend. This actually was inherently an extension of another academic group's project, an existing model. And it really just amounted to like writing some easy Python scripts that added that new information. It was super easy to parallelize this work for different parts of the extension, different extensions here between me and the other authors. And I think actually what was the most challenging extension, an undergraduate of mine, actually implemented in an order of weeks. So compare, an order of weeks from an undergraduate to 2.5 years with a PhD student and an undergraduate. That's amazing. Um, also, a lot of these scripts were really like simple and fun. I have a kind of funny example here, but I was actually writing this, or I started this work as I was writing my PhD thesis. And there was one day when, I would just take a break by writing some of these scripts because they were that much fun to write. One time I got so excited that I was just going to go and write one of these quick scripts, really quick kind of returns on investment. And in between drafting my thesis chapters, in my office, I decided to run over to my couch, was gonna, throw my feet up and program. I was so psyched, and then I just ran right into the couch and broke my toe. So like exciting enough to give me programming injuries. But the negatives also stood out, and they didn't stand out immediately. They really stood out once we started to evaluate these things, and when we were looking at, uh, you know, we needed to make scientific statements about like what is contributing, what is making these things better, how much better. When we really needed these results. So all of these negatives kind of blend together into just this mess of confusion. I'll talk about a couple different points here. Okay, so first of all, as we were evaluating this, we realized that different people in the same project group, we would train a model on identical data with identical parameters. Everything we were running like PyTorch in deterministic mode, and we'd realized that we were all getting different results. So we were really confused by this. And eventually we realized that our files were loading in different orders using the same like interface to load files. And it turns out that was because then the username of the user who was running the training script would impact the file order. So we'd all get different file orders. The file orders impact the results of training. We all get different results. We also found a non-determinism bug in PyTorch running in deterministic mode. And where just like the loss function calculation was non-deterministic. And it turns out that this was undocumented non-determinism in some underlying NVIDIA code. We also found that, with regards to figuring out like why things work, it was really hard. Some of our combinations of extensions if we put them in the same model, would mysteriously work kind of poorly. Even though if we put them all in the same model instead of just a couple of them, altogether, they would help a lot more. So we don't really know why. And we still don't have answers for this. And when I talk to people who do a lot of work with language models or even machine learning more generally, people just told me, "Oh yeah, that's just life. Like that's just how things are." And if that's how things are, I think that's really concerning. Um, and so there's more of this in that paper. There's a discussion section on the development process, especially. But this didn't deter us from doing more work in this space. So, for example, the Proofster project, we were trying to address a little bit this problem of understandability. Like, if you can't completely understand what's going on inside the language model, at the very least, we can give you a nice interface to understand the search process around it and the thing that it produces. So this is a web interface as well as a Coq plugin, and you can just state your theorem, press the button, and then it will try to synthesize a proof using one of the models that we developed on the back end. Really, here, you can actually kind of step through the proof in the web interface. What's really cool is that if it fails, then you can actually like look at the search tree, all the tactics that it tried. Um, so it's a model combined with a search process. You can go and look at the failed search tree. You can click around, and maybe you find a path that looks promising or something that it wasn't quite doing right. Then you can kind of take the proof from that point, give it a little bit of a hint, and then run it again. And we found that this works pretty well. Uh, we also looked at extending this to new tasks. So this actually was a collaboration with Radiance. And, we're looking at proof repair. Because proof repair had all these trade-offs in the traditional world, we really want to get machine learning tools for this. And so, here we built an actual data set for proof repair models for Coq using real proof repairs by proof engineers. This was a huge infrastructure undertaking. But we are training repair models based on this, and I'm excited to see like what these results are. I think one of the more interesting things that we did is this project Baldur. So this is a collaboration with this is work that we did over the summer at Google with Emily First. Is the first author here. She's now a postdoc at UCSD, and Marcus Rabe, as well as Yuri Brun. And this is actually an ESEC FSE like distinguished paper this past year. But this is actually using large language models now. And the idea was like, maybe we can just cut out the search process rather than have this kind of tree search. Like, how well do these models actually do at just synthesizing entire proofs? And so we took this Minerva model, which is a model from Google that actually is trained with a lot of natural language proof data, things like archive papers. Um, and we used it to, we fine-tuned it to formal proofs, and then we used it to synthesize proofs in Isabelle Whole. So this is a proof assistant that's a little bit different from Coq, but like some similar ideas. And then we evaluated it on this PISA data set, these theorems in Isabelle Whole. Already, despite the massive scope, again, of these data sets, of the evaluation suite, we found that it did pretty well. And we actually did some pretty fun things here where we looked not just at generating proofs directly, but also at whether we could get these models to use the error messages from their failed attempts that the proof assistant gives it to kind of like learn to repair its own mistakes. And without repair, it was able to synthesize whole proofs for 47.9% of the theorems in the data set, whereas search-based approaches would prove just 39%. Now, we also found that if we let it repair its own erroneous proof attempts with the same amount of work using inference, then it would actually prove another 1.5% of this data set, boosting it even more. And we also saw the benefits of diversity again. So we combined Baldur with Thor. So Thor is a similar tool, but it combines a large language model with a search procedure, like a tree search, as well as a hammer, a different kind of symbolic proof automation, like traditional proof automation, that's able to just solve certain theorems like pretty much automatically. That combined all three of those. Um, and we took Thor and we used it alongside Baldur together. And together they were able to prove 65.7% of the theorems in the data set, which is way more than either of them could prove alone. And it's a lot. So they kind of would, again, proving different things. Here we see not just the benefits of diversity in models, but also the benefits of diversity in techniques. Um, which I think is kind of cool. And we have this oracle, we can check things. So we can just run these together. So you can find more about all of these inside of the papers. But these kinds of trade-offs did continue to show up over and over again. Now, it is worth noting that there's a degree to which this doesn't matter. Uh, it doesn't matter that much that things are not super predictable, not super dependable, because we have this small logical kernel, this separation of concerns, and this thing that's actually checking the proofs in the end. So, some of these negatives do not matter too much because of this de Bruijn criterion. Our automation is safe; it doesn't touch the kernel. But there again, just a few like negatives here. I think really this makes the development process like for building any of this automation and using it kind of suck. Like it's just pretty hard to deal with this lack of predictability, lack of dependability. If you want to understand anything about why these work and how to make them better, and I'll get to this at the end, but I I assume here that we already have a specification. Now that's great, but in real life we often don't have that specification ahead of time. That's part of the development process of writing these proofs is figuring out what correctness even means. And I'd really love for these tools to be able to help you not just prove things, but also specify them. And for that to happen, we're really going to need to deal with these problems of lack of predictability, lack of dependability, of being able to understand what's going on. So I would really like to get the best of both worlds here. And I have some work in progress on this. And I think again, there's some degree to which like what we're doing when we use language models to produce a proof and we use this small logical kernel to check the proof, this is already neurosymbolic. It's already getting some of the best of both worlds, already bringing these two things together, this dependable logic checker and these completely wild language models. But I would like even more of the benefits of both kinds of automation, not just for checking the proof, but also for producing the proof. And I think there are two observations that kind of power a lot of my ongoing work here. So the first observation, mostly from Baldur, is that we can actually do fairly well without any kind of search at all. So maybe what we can do is still get the benefits of search, but actually move it up to a higher level than before. So we're not searching for tactics. Now we're searching for things like what is the next action I should take? What tool should I use? And maybe we can get better results that way. So, we're looking at moving the search process up in abstraction over what it operates over. Now, what I mean by search process here, I didn't quite go into this before, but if we have a tool that is doing kind of tactic prediction, then often that is combined with a tree search that does some backtracking. So, here it's trying to prove list for all to app. It tries some tactics. Some of those don't get it anywhere. Eventually, it'll backtrack, keep going, and hopefully, it finds a path that actually works. It's a really traditional, like tree search process. Um, now, what we're doing here is like, what if we think of these nodes not as tactics, but like this is based on some of an AITP like abstract where we let it like interact with the proof assistant, and we start thinking about now. Um, about having these nodes be just high-level actions. So maybe it starts off trying to prove the theorem, and then it decides to, decides it's how much you want to ascribe agency to these things, but it will try looking up a definition. So it interacts with the proof assistant by actually calling the command that will let it look up a definition, get back that definition. Maybe that definition gives it more information. It tries to write a proof using that. Um, and then maybe that proof doesn't quite get it there. So maybe it tries to revise it. Or maybe it tries to call another model that's like a critic that will actually give it feedback on its proof attempt. And maybe that whole path doesn't get it anywhere. So maybe it tries to run a tool that does premise selection, that actually looks for lemmas that will help it, prove this theorem. And then maybe it uses that premise to write a proof, and then maybe that gets it a QED. This kind of matches how like a lot of people interact with these tools. And here we can still do backtracking, but we're just kind of moving the search process up. So it's no longer about tactics. It's about these high-level actions. Now, there's some challenges here. For example, like we found it hard to get meaningful criticism from another model to actually, give it feedback on the proof. This whole thing could cost a lot of money, and context size has been really limiting. We often have to kind of take just parts of the information that we get back from the tool and encode them in a smart way because otherwise it's just too much for the model to handle. But despite all that, we've had some really promising results so far. So I'm excited for when we can, finally publish the result of this. Another observation that I've seen in work so far is that diversity is really helpful. Diversity in models, diversity in techniques. It seems to be, people spend so much time chasing after the one perfect technique, the one perfect model, whatever it is. But it seems like different models, different techniques, they just prove different things. And I really think this is kind of fundamental. Um, and and I think it's good because we can take advantage of this. Like we can bring these things together. We can use this diversity to our advantage. And so this is why I've been doing a lot of this, like why I'm so excited about training these models for proof repair, is because my hypothesis here is that the language models that we train or fine tune for proof repair, these are going to just fundamentally prove different things, repair different proofs from the kind of traditional proof repair techniques. I'm excited to see how these things come together. And finally, that brings me to opportunities, like what I think is next and what I would like to see. And I really think the big thing here is that throughout the talk, I've assumed that there is already a specification. We already know what it is we want to prove. But you know, I really think these language models, one of the things that they're most promising for is that they could help people specify things. For example, they're already pretty good at this test called auto-formalization in mathematics, where you take informal mathematics, like things written on paper, um, and actually try to formalize them into theorems that you can prove with a proof assistant. Maybe you even translate the proof or part of the proof. This has shown a lot of promise already. Um, so, I think these could help people specify their software, which is one of the hardest parts of actually writing these proofs. Now, here, I think we get something that is both extremely risky and extremely promising. It's risky, because this specification is not something that we can just check. So I'll talk about this a little more. But I kind of lied to you a little bit when I said like first you write your program, then your specification, then your proof. I think in real life these things actually like have a lot of interplay. People are moving back and forth between different stages here, refining their program specification and proof all at once. This whole process of thinking about what it means for your proof to your program to be correct and whether your program satisfies that is intertwined with programming, and it's intertwined with refining what correctness means. And I think that we can get at someday, I would love this, we really should be able to get help at every stage of this process. So not just help writing this proof when you already know your specification, But also, say you're writing your proof, you realize the specification isn't quite what you want to go back and refine your specification. Can't you get help with that? Or, not just like, maybe you have your program written and maybe it can suggest some specifications for you. Or maybe that specification, or maybe when you're writing your proof, you realize your program is wrong. You want to go back and fix your program. Maybe your specification is not quite what you want, and you realize, or maybe your specification actually helps you realize something is wrong with your program too, and then you want to go back and fix your program. Like all of these things are really tightly coupled in real life. The real development process for proof engineers moves between these stages back and forth as they're going. And I think we want help at every stage. So in the end, we get a proof of, that the program satisfies the specification that really matches our intentions, that matches what we want. uh, and uh, what's hard here is that de Bruijn is really helpful for once we have a specification, making sure that the proof satisfies it, but it assumes the specification is okay. And we don't have an oracle that's actually going to check the specification being okay. What does that even mean? It means fundamentally, I think, that it matches the user's intentions. It matches what is really wanted, and the user might be slightly incorrect about what they think they want. So it's a hard problem. Um, and so I think, and this is like a challenge I want to leave people with. I think the most important problem right now, in this space, is to figure out like what tools um, can actually best help users make sense of a generated specification that comes out of one of these tools. And I don't think the problem is, do we have these tools? These tools might involve generating tests based on a specification. They might involve using things called theory exploration to find other, lemmas that are implied by the specification and presenting those to the user. I don't think the problem is that we don't have these techniques. I think the problem is that we don't know what is useful to users. This is fundamentally an HCI problem. We need to know what information presented in what ways is going to best help users ensure that these specifications really like match the user's intentions, because like the user could be misled by a specification that comes out of one of these things. They might think it is what they want when it's really just a fancy way of saying something trivial or very partial or something irrelevant. We need to know what information it is that actually helps users ensure these specifications match what they want. And then I think we can get to this place where lots of people can really easily build these kind of more trustworthy software systems by verifying these systems without all these challenges. So this is the challenge that I want to leave people with. And with that, I can take questions.
Awesome. I'll give you a little round of applause. Unfortunately, there's, the audience can't be heard, but thank you so much for that talk. If anyone has any questions and you put them in the chat, I should be able to see them. And I guess while we wait for that, this is maybe not a question directly aimed at your research, but obviously it's kind of cool that you've been working with language models, both small and now large, for a relatively long time, or at least since before ChatGPT was released in late 2022. So, you were already doing some research in this area while the world has now begun to focus on LLMs, and there's obviously this massive acceleration happening now. So I just wanted to ask what your experience has been like already having a use case for language models when all of a sudden all these corporations have begun putting a massive amount of resources behind the technology, and many people are trying to play catch up.
Yeah, it was maybe exciting, lucky, and scary, as it always is. Um, I did get a sense, like even though I wasn't, it wasn't like ChatGPT that had come out. Um, OpenAI had released a version of Codex, the coding model, to like a limited audience at the time. At the time that I was doing like the earliest work that I did on machine learning for proofs, and I remember like I remember playing around with it. I remember wondering how the world was going to change and being terrified at the amount of like bad code that people were probably going to use these things for, and then also being excited about, well, maybe I can, use these. Maybe this is actually an opportunity to help people write correct code if we can actually help with this process of verification. Um, yeah, so it's always hard to keep up with this field with what's happening, but um, I don't know. It definitely kept me going and is a motivation for continuing. I think right now probably half my work is on the traditional automation and half of it is on kind of language model based automation.
Yeah, cool. We have a question here from Grant Jurgensen. What is the motivation for using language models to generate tactics as opposed to directly generating proof terms? Would the latter approach also be viable?
Yeah, that's interesting. I think the motivation is mostly just that tactics tend to be more natural because they were designed to be more natural. So they tend to be more similar to natural language proofs, which means like, I mean, again, it's too hard to know what's really going on inside the model, but our hypothesis is that because these kind of are similar enough to proofs that are written in natural language, it's able to kind of repurpose that data more easily. Whereas for proof terms, I think you need a lot more proof term data to do well. Um, you could just as well do the proof terms directly. And the proof terms are eventually being generated when we have a tactic script, of course. But yeah, you could do the proof terms directly. I think I know some people who have tried this. I do not know how successful they were. It does seem to me like it's a harder problem when you're using a, a language model, but
Yeah,
not for certain kinds of traditional automation. I will say that, like the proof repair stuff, I actually transform the terms directly and then use a decompiler to get tactics from that because it's super hard for traditional techniques to deal with these tactics. So again, like opposite trade-offs.
yeah. All right, I have another question here from Julian Van Egg. I guess two questions. Can you share any preliminary return on experience on generating formal specifications from informal English ones using language models? And do LLM methodology have any impact on performance of the extracted code?
Interesting. Okay. Um, Yeah, so I guess on the first one, I haven't done serious work on auto formalization yet, but I think the word that I would look up is auto formalization because there's a lot of kind of work in the space that we've cited. Um, and probably, I think one of the really, really cool papers in this space is draft, sketch, and prove. And it combines a whole bunch of things. It takes kind of informal um, like sketches of proofs and so on, and then uses those to like generate. There's an auto formalization process, and then to fill in the gaps, it uses traditional proof automation to kind of dispatch those gaps. So it's a really nice, like, along with this theme, kind of best of both worlds thing. Um, but yeah, I would look up the word like auto formalization, and you can see what is kind of covered in that space. I'd say so far it has, like, the work I've seen on this has been really promising, but it's mostly been for mathematics, and um, the hard. I think it's really hard to find kind of data for the informal specifications of software and their formal versions. And once we have more of that, then maybe we can kind of test that out a bit more. Um, I also think what we want to use to generate specs for programs shouldn't only be the like informal statements of it. Like that might also be hard. I think it can also be things like executions of the program, feedback from the user, test cases that they write, lots of other information. Okay, second question there. Um, an impact on performance of extracted code. Um, I'm not quite sure. I mean, so okay, I guess when I'm doing traditional automation, this is a huge concern. Like there are some ways of doing traditional automation where if I'm going to change a program in any way. Like in repair, we might change program specifications and proofs all at once along some well-defined line. And if we do that, um, we have to be really smart to stop the performance from completely like exploding. For language models, I think because they actually tend to prefer natural things, I haven't seen a huge performance blowup of what's actually generated in the end. Um, Instead, you might see a performance hit to the automation itself.
Cool. I think we're not going to get through all these questions. I do see a lot of people saying, great talk, very interesting,
Thank
and
you.
thank you. But maybe we can do one more. So this one's kind of long. So let me ask this one from Ahmad Ridley. Once you have a verified correct proof for a specification, if that specification changes, can this hybrid approach improve to reuse parts of the proof for previous specification?
Yeah. So this is part of the idea of like proof repair in general. It's like part of the problem that we're trying to deal with. And I think like I think my hope is that this will help significantly for a couple of reasons. One is that like this traditional proof repair only helps in this situation if the change in specification is like uh, is well defined along some class of changes that we've already decided to support. And it turns out there are just many ways to change things, and not all of them fit neatly into this. And even if they do, it might be hard to describe how they neatly fit into this. Um, and so I think we can start to handle kind of really like, yeah, a lot of the really repetitive changes that people do. I suspect that these things will be very good for. Um, I also think uh, um, here we can we've seen a lot of success with like in context learning. This is also one of the takeaways from Baldur, is that say you have a file with a whole bunch of like repetitive lemmas that are slightly different. Like the model tends to be pretty good at reusing information from one of those lemmas, one of those proofs for another one, and kind of adapting it across those changes. And so I think you could probably see something similar. I expect to see something similar with repair when those lemmas are no longer kind of alongside them. They just maybe you keep the context of some of the history around. I think that that will help a lot in those cases.
Cool. Thank you. Well, I think we're at time. I guess technically we have a 15-minute break, so I don't know, Talia, do you want to answer a couple more questions, or do you have to run?
I can do one or two more. I think if
All right,
it's yeah.
let's do one or two more, and then we'll give everyone a break before
Okay.
the rest of our agenda. So Jonathan Aldrich asks, um, I guess the question is, maybe I'll let you read it. The first proof repair example, it struck him weird that the proof assistant would depend on the order of cases in a data type. Um, and so in this tiny example, is there a larger insight here where the design of a proof language can make proofs more or less fragile?
Yeah, that's a good point. Like it is deliberately a toy example, but like there are some proof assistants that don't depend on that. Like I'm pretty sure that the AGDA proof assistant treats the order of constructors as irrelevant. Um, you know, so I think it is an important point. There's a fundamental trade-off between design and then automation for repair, where like design is kind of a proactive thing, and repair is like it's retroactive. It's when something already has been designed in a way that wasn't perfect. How then do you fix things? Um, and I think in real life we need both. We want to design things to be like really resilient, to changes as much as possible. But on the other hand, you're not going to be able to foresee every single change that you could ever think of, every use case. Change is constant no matter how well we design things. So yeah, we want both.
Yeah. All right, and let's end on this one. So Stuart Matthews says, "Great talk, thank you. Can you say a bit more about what kind of inputs you train the LLM on? Is it natural language or proof tactics scripts in the DSL?"
Yeah, that's so. I think for Baldur, the Minerva model was trained on natural language proofs to begin with. A whole bunch of like archive papers, like lots of data on natural language proofs. But then we fine-tuned it using some of the proof scripts inside of this Isabelle, using this Isabelle proof assistant. The fine-tuning, like our hope and the idea, and again we still don't know completely, but it seems anecdotally like it's able to take advantage of a lot of the pre-training data on natural language proofs and kind of draw some connections to a smaller amount of data on formal proofs, because we don't have as much data on formal proofs. We've been at it for a couple thousand fewer years.
Gotcha. Awesome. Well, thank you so much for that awesome talk. And hopefully we'll see everyone back here in 10 minutes, 11:30 Central after a break.
Thank you.